Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Derek Sears, who's come across to us from NASA Ames and the Bay Area Environmental Research Institute. Derek did his bachelor's at the University of Canterbury in Kent and his PhD at the University of Leicester, where he was studying astronomy and geology on the edge of both of those topics. His topic was meteorites, which we're going to hear about today. He did a postdoc at Birmingham and some other locations as well, and then came across to the United States to be a visiting fellow at UCLA. And then in 1981, he joined the University of Arkansas and helped set up create their space studies center there for 30 years before, where he was the chemistry and biochemistry division, and he was the W.M. Keck Professor of Sciences and Planetary Science, of Space and Planetary Sciences. And then last year he came back to NASA Ames, and that's where he is at the moment. And Derek is the author of 3 books. One is entitled Thunderstones, is a history of meteorite falls in Arkansas. The nature, and another book, The Nature and Origin of Meteorites, and he's just published another volume, The Origin of Chondrules and Chondrites, which is what the topic of this talk will be today. Derek was the editor of Meteoritics and Planetary Science from 1992 to 2001. And his research has revolved around several topics. Some of interest are natural and induced thermoluminescence of meteorites and lunar samples, chondrules from meteorites and Apollo lunar samples, astatite chondrite meteorites, asteroid surface processes, microgravity experiments, and Mars-related measurements and experiments using vacuum chambers. So today we're going to hear about origins of chondrites and chondrules. So if you'll join me in welcoming Derek.
Thank you very much. Well, thank you very much for that very fine introduction, Adrian. He told me he knew nothing about me, and then he talked for 5 minutes. Impressive. Thank you also for inviting me to give this talk. This is a great joy. I arrived in the Bay Area last August 1 was my start date. I think I actually physically arrived on August 14th, and immediately felt the need. I had a lot of great friends in the space science astrobiology division, so I felt at home in that respect. But getting to know the region was fun, and I found out about the SETI seminars, so I've been coming very regularly, enjoying them very much. So I appreciate Adrian's efforts on that front too. I've never known a series so well organized. I think Adrian does a remarkable job. I hope he gets well paid, right? But one of the things Adrian did, which caught me completely by surprise, he introduced me to peanut butter and jelly sandwiches. I'd never eaten one until I came to these talks. And now I really rather like them. So I ascribe the turnout to the peanut butter jelly sandwiches. That was a joke that Dale fed me earlier on. So it's great to be here. Thank you very much for this opportunity, and I hope you get half the enjoyment out of this that I've been getting out of the other talks. This is a somewhat controversial topic. It's a somewhat old topic. People have been arguing about the origins of chondrules and chondrites, as far as I can see, from about 1803. So forgive me if this appears to be a somewhat out-of-date talk. It's the nature of the material. And that's one of the frustrations, that we've been studying these things so long and so hard, and there are days when you wake up and you think, crikey, where are we going? And actually, John Wood, who was astrophysicist petrologist at the Harvard-Smithsonian Institute for Astrophysics, actually gave a talk at one of the big conferences a few years about a few years ago about the tight-lipped chondrules. We stare at these things forever and they will tell us very little. He got himself into a lot of trouble for that because a lot of people have worked very hard. But it is a topic that's been around a long time and it's waiting for a solution. And what I'm going to argue today is, in a sense, the solution's been staring us in the face for at least 5 decades, and it really hasn't dawned on us, or didn't really dawn on me, until we started to get into the space program and we started to get missions to asteroids. We started to get out there and started to see what some of these objects we were theorizing about were really like. Then I think, at least in my mind, things started to click, and I think there's still a lot of the community hold different views, but I think there's a lot of the community that are beginning to sort of have ideas similar to mine. So I'm going to pitch these ideas to you this afternoon to see how they fly. So chondrules and chondrites. I'll tell you what they. I suspect most of you know what these are already, but I'll give you a quick refresher. Starting with meteorites, if I can get that. There we go. Most of you will have seen this. This is the Peekskill meteorite. Where's it gone? Oh, there it is. We went past a lamp. And you can see it coming down through the atmosphere. You can see they come into the atmosphere as something on the order of 40 kilometers a second velocity. That's a heck of a lot of energy, half mv squared. That's a lot of energy. So they've got to get rid of this cosmic energy in a matter of seconds. A typical flight time is about 20 seconds, 10 to 20 seconds. And I enjoy that so much, I will do it again. And I get a rush out of this even now. I mean, I can't tell you how many times I've seen this, but I get a rush out of it. You see the thing breaking up, you see the different fragments. These things are full of fractures. So the first thing they do when they get into the atmosphere, starting up there at 70 or 80 kilometers, is they start falling apart. And each part produces its own ionization trail. People have said that the ratio of the meteorite to the fireball is about the same as a football to a football field. So when you're looking at this object, what you're looking at is the ionization volume. That's the atmosphere absorbing all this energy and being taken up to many thousands of degrees, and it basically is a plasma, and it produces a huge amount of light and sound and other effects. Then as the object reaches what's called the retardation point, about 8 kilometers, 9 kilometers, it's basically stopped. It's lost its cosmic energy at that point, cosmic velocity at that point, and it falls like a block of concrete, may be affected by the wind, may have a little bit of residual vector to its movement, but basically they hit the ground like blocks of concrete falling off an aeroplane. So they will bury themselves a few feet. In this case, it buried itself about 9 inches into the back of this Cadillac. This actually is a car that was bought by the owner, who was a student at one of the schools in New York, undergraduate student, Elizabeth Catloss, something like that. You should know, right? Something like that. She bought the car for $100. She sold it for $10,000. So there's money in this game, okay? And let me show you the next. There's the same car with the meteorite. This is the Peekskill meteorite, about 7 kilograms, and she sold the meteorite for $100,000. And it's a very common type of ordinary meteorite. That's an oxymoron. Meteorites are not ordinary, but we call them that to distinguish them from the ones that are not so ordinary. In England, we call them common chondrites, which I think is bad. I don't like that term. And so here's some mug shots of my kind of meteorite. Okay, these are all these so-called ordinary chondrites, the commonest type of meteorite, and you can see they all look somewhat similar. You see the light grey interior, the black coating, which fascinated me when I was a grad student. The whole chapter of my PhD thesis is about this fusion crust, and all my colleagues say, why? It's just the heat zone, the heat-altered zone, but I love this stuff. And then you can see how sharp the boundary is here between the crust and the interior. Is a better example over here. You see this beautiful thin sheet of fusion crust, that's the glassy surface, the melt surface. So you can see from there that the heat really doesn't penetrate very far. As a matter of fact, a thick crust would be a millimeter, and a thin crust would be a tenth of a millimeter. So these are really thin layers. And you can go about a centimeter or two into the meteorite, and that meteorite saw no heat at all coming down through the atmosphere. So it doesn't surprise me at all that the people who first worked out the theory of these things coming through the atmosphere were the same people that designed the Mercury spacecraft heat shield. Same set of equations. I think that's cool. This is not an ordinary chondrite. This is Peter Janiskin's meteorite, which we call Sutter's Mill, which is actually a carbonaceous type of meteorite. So it really doesn't belong on the slide, but it's so newsy, it's so of the moment. So all right, important disclaimer. What I'm going to talk about are these common chondrites. I am not going to talk about the weirdo meteorites, those that come from melted bodies, the basalts, those that come from Mars or the moon. We have about now, I think, 60-something meteorites that we know are from the moon. We have about 60 meteorites that we know, a very similar number, kind of by coincidence, from Mars. So I must smile when I think of, you know, whatever it was, the $40 billion that was spent collecting Apollo samples, and now we have 60 meteorites from the moon. But I think even more when we talk about getting meteorites back from Mars, getting samples back from Mars, and all the agony that's causing the folk at headquarters and all the policy writers and the National Academy of Science type people trying to figure out how to get samples from Mars. And we actually have about 60 meteorites in our museums. Some of them are in our labs from Mars. So we have Mars rock on Earth. Now there are ands, ifs and buts. There are lots of reasons why you'd want the sample. Anyway, today I'm just going to talk about these, my pet love, these chondrites. Other than my wife, that's a different story. And I'm going to start by giving you some of the basics, okay? Number one, they are old. We have known since the early 50s that you can date these rocks. Here we have a radioactive dating method. Rubidium-87 decays to produce strontium-87. If you take out the chemical noise by normalizing to strontium-86, that takes away some of the chemical effects, then the older this rock, the steeper this line, okay? So we can get the age out of these isotopes, and the age comes in at 4.65 billion years. That's pretty old, yeah? If you do a whole rock dating, as it were, of the Earth, you get 4.65 billion years. If you do the same thing for the moon using the Apollo samples, you get 4.65 billion years. If you talk to the astronomers and the astrophysicists about the sun and the ratio of helium to hydrogen and the stellar evolution, and you try and get an age out of that for the sun, it comes in at about 4.7 billion years. So 4.65 billion years is the age of our solar system and everything in it. And these rocks, these pieces of rocks I've just been showing you, these pale grey rocks with black fusion crusts, they are as old as the solar system. Very important. If we look at the composition, we come up with something equally startling. I think it was starting in 1880, 1890. Henry Norris Russell, famous for the Hertzsprung-Russell diagram. Everybody knows about the Hertzsprung-Russell diagram. Russell, prominent American astronomer, took the Fraunhofer lines for the sun, tried to calibrate them using laboratory measurements with arc jets, tried to work out the relative proportions of the elements, came up with a conclusion which I think very few people believed at the time, which was that the sun had the same composition as the meteorites, based on 5 elements. A decade or two later, that was repeated by a Swedish geochemist, did it for 30 or 40 elements. Now the conclusion was just irrefutable. The meteorites, these common chondrites, these grey rocks that are falling down through our atmosphere, have exactly the same composition as the surface of the sun. Well, nowadays, using this plot is from 78-ish. You can have 6, 7, 8 orders of magnitude in the elemental abundances, and you compare the sun with the meteorites, and you get a straight line that most experimental scientists would give the right arm for. Okay? Now, as you get to the elements which are hard to measure, these very, very low abundances, you start to see some noise. But by and large, and lithium is a problem, but we think we understand. But by and large, the composition of the meteorites is the same as the composition of the surface of the sun. So when I talk to my students, or when I used to talk to my students at Arkansas, I used to say, imagine going and grabbing a piece of the solar photosphere and bringing it down and putting it here in this lecture room. This is what you'd get. Now you're missing the things that don't condense at room temperature. So we're not missing, but we're a bit low on hydrogen, oxygen, nitrogen, the inert gases. The things that are not solid at room temperature, we're missing from the meteorites. But other than that, you've basically got sun stuff. I mean, that's what it is. So it's very old, and it has the same composition as the surface of the sun. But Urey and Craig in 1957, Harold Urey is the Nobel Prize winner, discovered deuterium, very prominent chemist. Went through 350 odd analyses of meteorites, mostly ordinary chondrites, and found that there were subtle differences from the solar values. To a good approximation, they're all solar. But when you look real close, you see subtle variations. And their way of presenting this was this plot. Another thing that's interesting about the meteorites, and that was realized right from the 1860s, 1870s, is that in most cases, on that previous diagram you saw chalcophile, and did you see that? Siderophile, lithophile. Most of the time, the elements behave like they're expected to behave. Siderophile elements, siderophile, iron-loving, lithophile, stone-loving. So to a great approximation, the elements go where they belong, into the metal, into the sulfide, into the silicate. Iron is an anomaly. It's not only a very abundant element, but it also has a schizophrenic behavior. It tends to go both into the metal, get metallic iron, and it goes into the oxides, you get silicates, you get iron-silicon compounds. So it's wonderful from a chemistry point of view, because now you can write an equation. You can have iron on this side and iron oxide on this side. You can get the elements to balance, and then you can go to the thermodynamic tables, and you can do chemistry. If any of you have done Chemistry 101, general chemistry, you know how to do this. And out of the amount of iron in the oxide and the amount of iron in the metal, do the equations, work the thermodynamics, work the calculations. You can calculate things like how did the chemistry go, what was the temperature of the reaction. So from a chemical point of view, having iron in two phases is really cool. So that's what's going on here. So here we have all the iron that's in the metal. Here we have the iron that's in the silicates. We also have the sulfides, and if you've done Gen Chem, you know that sulfur is a lookalike for oxygen. It's next stop down in the chart, right? So sulfur is like oxygen, but there's far less of it, and so you tend to get oxides wherever there's oxygen around in preference, but you always get some sulfides. So anyway, what this diagram is telling us is that not only do you come away from the solar iron value, which is that diagonal line, you drop down here. It's as if you've taken iron away from the silicates, removed iron, but you've also got this spread of oxides. So here you've got the metal is all in the iron is all in the metal. Here the iron is all in the oxide, and that's like a mixing line in between. So you can see oxidation is what the chemists say. You've got oxidation trends here, reduced, unoxidized, and then highly oxidized here. So the meteorites are showing us subtle variations from solar and a big variation in oxygen. And this is going to be a big part of my story. How did we come about removing the metal from the silicates? And how do we explain the fact that so many meteorites are highly oxidized? Okay? Now, why do we care about how many meteorites are really oxidized? Let's pause for thought. We'll come back to this theme again and again. Rocks are 4.7 billion. They have the same composition of the sun. So a lot of the scientific community have got into their minds this notion that we're dealing with an astrophysical environment. This is the dust that formed the solar system. It was an astrophysical environment. What do we know about astrophysical environments? They are predominantly hydrogen. Right? The hydrogen-helium ratio in the cosmos is a 75-25-ish. And everything else is less than 1%, right? You all know that. So these things formed in a hydrogen-rich environment. So what does oxygen do in a hydrogen-rich environment? It forms water. It does not form silicates. So any reasonable concoction in our minds of how we make meteorites in a astrophysical environment, we should not get any oxides at all. So something happened to these objects to make them more oxygen-rich. I'll come back to that. All right, long story, okay? I kind of like this slide. I put it together just for fun. All the prominent chemists and geologists who worked on meteorites and given us the classes as we know them today. And what strikes me about this is the fact that there are so many prestigious chemists in the story. This is Lavoisier, who gave us basic chemistry as we understand it. You know, this idea that molecules have mass and atoms have mass, so we can do calculations and mass balance. So he's got to be the Isaac Newton of chemistry, right? Anybody want to argue? Jöns Jacob Berzelius, one of the giants of chemistry. He actually gave us organic chemistry, but he did a whole bunch besides that. He discovered that ions were important and that you could explain chemical reactions in terms of positive ions and negative ions, all this good stuff. Back in 1834. Okay? So he's one of the giants of chemistry, but I think he's important because he studied meteorites. Back in 1834, when the only way to do a chemical analysis of a meteorite was with acids and test tubes, he actually worked up the wet chemical analytical method that is still the best for determining bulk composition. What's ironic is that there's nobody doing it anymore because everybody thinks it's old-fashioned. But the truth is all these instrumental methods do not give you a complete analysis. They give you a bit and a bit and a bit. So if you want a complete analysis, you've got to go and read up on Berzelius from 1834. So he's in the story. And then we've got Pierre Araduri at the end here. And I could go through and pick some others out. Very prominent people. The Sorby is up there. He gave us thin sections and microscopy. He gave the microscope to the geologists, in effect. So he founded petrology. So all these sorts of important people. I'm just making the point that classifying meteorites or sorting out their chemical trends has been a long, hard-won process. And I think we're there now, but it's been a long. This is what I mean when I say I think we're there. All right, I don't want to swamp you with all these sort of geochemical details, but I just want you to get a couple of things out of this. This is the composition of chondritic meteorites, of ordinary chondrites, or chondrite, the solar stuff, meteorites. And what we've got is abundance here, and we've got element here. And we've got the most refractory element here and the most volatile element here. Refractory means highest temperature material. It takes high temperatures to melt it, takes high temperatures to evaporate it, so it's the most robust. It's what you make the linings of furnaces with. It's ceramics. It's what you make heat shields with. Okay? And then down here you've got the sodium, potassium, highly volatile elements. Okay, we make sodium lamps because sodium is so volatile. So you have this volatility sequence here. We have one over here. Here we have the siderophiles and the chalcophiles. Chalcophiles, the sulfide loving. Here we have the lithophiles, the stone loving. So we sort the elements out into their geochemical categories. And then what you see are quite distinct patterns. You see these parallel patterns here for the different types. See that we're all basically solar. That line is solar. Right? So we're tweaking it. We're looking at little differences from solar, but we're seeing systematic patterns. We're seeing a volatile loss. So we're seeing these more volatile elements are depleted, except in these guys where they're flat. And in this guy, there's some evidence it actually goes up. That's weird. I wonder if those data are okay. Now, if you come over here with the sterophiles, volatile patterns vary from class to class, but they're always there. Now, I'll say more about this in a moment, but if you look at a meteorite, like any object, is made of the stuff it contains. Is that a profound statement? You'd be amazed how many times I've read that in scientific papers. We conclude that these meteorites have this because they've got chondrules in them. Yeah! You know. So one of the major components, 80% of the silicates in the most common meteorites, are made up of these things called chondrules. Chondrule. The word actually comes from the 1860s, from the Austrian petrologists who took these meteorites apart, and they found these little beads in them. Actually, the story goes back to a Brit, well, a Frenchman working with a Brit. In 1803, Edward Charles Howard, who you've all heard of, right? Brother of the 12th Duke of Norfolk. Does that mean anything? No, that doesn't ring any bells? No, we all know the Duke of Norfolk and his brothers. Well, go back to 1803. The brother of the 12th Duke of Norfolk was aristocrat, more money than he knew what to do with, time on his hands, thought I'd be a scientist. This is what they did in those days. So he got the Copley Medal of the Royal Society for inventing fulminating mercury. Mercury fulminate, anybody know what that is? Pardon?
Yes. Explosive.
Explosive. What did you say? Caps. Yeah. You're sort of right. He's very right. Degrees of rightness. This stuff is so explosive. It's too explosive to use as explosives. So you use dynamite or gunpowder or whatever. But it makes a really good detonator. So it's used for detonators. It's still used nowadays as a detonator. So we had fulminating mercury. We had fulminating silver. And what Howard did was to create this stuff for the first time. He put it in a proofing gun, basically a flintlock pistol that they used to proof gunpowder. How much water could you put in before the gunpowder stops exploding? So and they do the same for proofing alcohol. How much water is there in the alcohol? Anyway, he put his fulminating mercury in the proofing pistol. And like an idiot, he held it up to his face, blew half his face off. So the only picture of him in existence was on that sheet, actually. I know this is going to take 2 hours for this talk. I have to be careful here. Oh, where's it gone? There you go. So this is him, Edward Charles Howard, one of my favorite chemists. Only ever appears in profile. He was a genius. He not only discovered fulminating mercury, he did the pioneering analytical work on meteorites. He invented vacuum distillation for sugar. If you want to purify sugar without messing it up, without burning it, you can vacuum distill it. And he invented that technique. And as a consequence of that, he invented the sugar industry. So you know how important the sugar industry has been in the history of the British Empire and the slavery in the Caribbean and so on. So he was one of the technologists that triggered Britain's love for tea and for sugar in their tea. I'm digressing too much. I control myself. All right. So these chondrules. Yeah. So anyway, Howard was working in London at the Royal Institution, I think, and the French Revolution was happening, and the prominent scientists from France, in as much as they had scientists in those days, the aristocrat scientists, flocked to London to get away from the reign of terror, and one of them was Jacques-Louis Comte de Bournon, met up with Howard, and Howard did the chemistry, Bournon did what we would now call the petrology. And he said, these meteorites from all over the world, Sir Joseph Banks had brought these meteorites from all over the world. He was the scientist with the James Cook, right? James Cook's exploration of the Pacific. And he came back to Britain, became the grand figure in science, and acquired all these meteorites, which he gave to Howard. And Bournon looked at them and said, every one of these objects, from wherever they fell in the world, from South Africa, from Portugal, from England, all had these curious globules. He called them these curious globules. And that was one of the key points in establishing meteorites as a serious scientific study. They really fell from the sky, because although they fell all over the world, they all had this kinky thing of these curious globules. They also had nickel in the metal and other strange things. So anyway, in the 1850s, the Viennese petrologists called these things chondrules, and that's from the Greek meaning chondrus, meaning a grain. So it's, I don't know if I want to call them grains really, but so the word stuck. So any rock that had these chondrules was called a chondrite, and so this is how we get the nomenclature. Unfortunately, we now know of chondritic meteorites that have no chondrules, but such is life. Anyway, pull out the chondrules, do the chemistry, and it becomes quite clear, and this is why I said earlier on about things are made of the components that, they're the properties of the components that they're made of. A lot of these properties are explicable in terms of these things. These chondrules also have siderophile element depletions, they have volatile depletions, and so a lot of these properties we're getting in the meteorites are because of the mix of chondrules you put in them. If you put a lot of volatile rich chondrules in there, you get a volatile rich class. If you put volatile poor chondrules, you get a volatile poor class. That's one thing. Okay. The other thing is this thing about varying the amount of metal. So I think we have two patterns that explain all you want to know about chondrites and their diversity and their origins and history. They contain these chondrules, which govern a lot of the chemistry. They contain metal, and the metal to silicate ratio has been monkeyed with, has been changed. So that's what my Chondrules and Chondrites book, the main theme was. How do we explain these two patterns that you see in chondrites? Because that is what gives you these classes. That is what gives you these very important ancient materials. So if you want to use these materials to learn about the early stages of the solar system, 4.65 billion years ago, you've got to. This is the information. This is what you've got to work with. Chondrules. As I say, the first observations are 1803, 1860s. We got the microscope, the thin sections, and looking at these things through a microscope. 1885. This is one of these Viennese petrologists. What was he now? He was keeper of His Majesty's mineral cabinet, which we now call the Natural History Museum of Vienna. And then we have G.P. Merrill, who was curator of meteorites at the New York, the American Museum of Natural History in New York. And they published these pictures. I believe these today are still the best pictures we have of these objects, despite all our modern digital techniques. So you can see they're generally speaking spherical. They have crystals inside them. Crystals of various forms. Here they're very fine radiating fibers. Here they're great big thick bars with a thick rim around the edge. Sometimes they're just individual grains set in a glass. One thing that characterizes all of these is glass. You see glass in all of them. So it's glass with crystals sitting in them. And that's a very familiar structure. That's a quench structure. That's what happens if you take some silicates, heat it up above the melting point, and then let it crystallize. The refractory components form the crystals, and the rest stays behind as glass. So you think glass, you think heat. Flash heating. Okay. So, and then Merrill published this paper with a similar array of these fascinating objects. And you can do the petrography of the chondrite, and you can see how important all these chondrules are. Here is a meteorite, 200 microns, 100 microns, sitting there, real sharp, crisp chondrules, razor sharp edges. You can see that this is some sort of a mixture. There's some sort of stuff collapsed down out of the solar system somehow and formed this mixture. Then you can see a trend here where the chondrules become less and less sharp until they've almost disappeared. Now, John Wood explained what this was in 1967. This is parent body metamorphism. Okay, on the parent body, which is a word that means nothing, right? It's the thing on which these things came from. There was some source of heat that baked them up and caused their compositions and textures to change. So that by the time you get up here, you get very little. You can see very little detail of the individual chondrules. They've all been smudged away. And we did a study using their luminescence property. Adrian mentioned that we've done a bunch of luminescence type studies. If you look at these chondrules under a cathode beam, under electron beam, You can make them glow. The nature of the glow depends on their chemistry and on their physical properties. Am I doing something wrong?
No, but it's a laser pointer.
Oh, that sounds fatal, isn't it? When people get laser pointers, everything goes wrong with their talk. The slides go in the wrong direction. So, all right, I think maybe it's something to do with the TV. So you can see the certain types of chondrule, as you metamorphose them, metamorphism is the geological word for heating without melting. Okay, so baking them without melting them, metamorphism. Solid state recrystallization, if you want to use the dictionary definition. So, okay, so here are the chondrules, and you see as they go up in metamorphism, they change color, they get a bit coarser in texture, start less easy to find them. The outlines get, but not only do we get this series here, we get another series here where a whole bunch of chondrules didn't glow at all, and as we bake them up, they turned into the same thing. And then we get a few chondrules that started out looking the same thing, blue with black grains, and they just stay pretty much the same throughout metamorphism, except that they lost the textures and so on. But the point I'm making here is we've got to see through metamorphism if what we're interested in is the starting material. So that's been a big problem for chondrite studies. But also the chondrules, which are an important part of the story and make up so much of the meteorite, are very diverse. Okay? These couldn't be more different from those guys. They can have different oxidation states. One can have a lot of oxygen, one can have very little. They can have a lot of volatiles. One can have one can have a lot of volatiles, one can have very, very little volatiles. So yes, meteorites are made from mixing chondrules with metal and other stuff, but the chondrules themselves can be really very diverse in their properties. Everybody with me? Yeah. Aren't you glad the slide projector worked? 5 minutes before the talk started, we could not get access to the PowerPoint. That's what Adrian made mention of, that the IT folks came to our rescue 3 minutes before I was due to speak. I had to disassemble my hard drive, which is kind of interesting. Now, next lesson, next point. Okay, chondrules, critical. Chondrule formation, metal-silicate fractionation. That's what we've got to focus on. We can make chondrules, okay, no problem. Right? We can take a silicate mixture that has roughly the same composition as the meteorite. We can do a flash eating, and we can make all the chondrules you want to make. And we can give them all the different properties that you want to have. It's a favorite sport of experimental petrologists in meteorite studies. You know, we'll go and make out a new set of chondrules. We found a new set of chondrules in this new meteorite. We're going to make them in the lab. We can do it. And we know pretty well what it takes. We can take these textures and we can convert them into cooling rates and heating temperatures. We can quantify the process that formed these guys. This has really been very successful work. Gary Lofgren at the Johnson Space Center, Roger Hewins at Rutgers, pretty much got it all worked out. Some work done at Albuquerque, hitting silicate rocks with a laser, making a spall of melts. And what's really cool about this picture is that as these melt droplets are splaying out from the point where the laser hit the rock, they release the energy that was put in them by the laser in the form of light, and you can see that as they cooled down and gave up their energy, they gave this luminous streak. See that? But you see this? Some of these droplets came out and didn't give out any light until something magic happened there. You see that? That's supercooling. What they did was to melt, and then you pretty much froze the energy in the chondrule droplet, and then when it hit some kinetic possibility, shall we say, it suddenly underwent the physical changes that gave out the light. It crystallized, or whatever. So we can actually see that some of these chondrules supercooled, and then they crystallized and gave out their light. So they just absorbed the light, just melted droplets, shot themselves through space, didn't give out any light until something went click and they crystallized. Nucleation centers or whatever. So some chondrules were cooling in equilibrium all the way, some of them supercooled. That's what we were seeing in some of those data, in some of those different types of chondrule. Some of them had frozen-in compositions, like they had been supercooled. They were supposed to be melted, and we'd done the supercooling experiment with sodium thiosulfate. You do that in your last year at high school. You did it, you've forgotten. Take sodium thiosulfate, put it in a test tube, heat it, turns into a perfectly clear fluid. That melts at a certain temperature. Melts at that temperature. I don't know what it is, 600-700 degrees or something. Melts at that temperature. Then you let it cool down, and it stays as a melt until it goes down to 500, 400. So the melting point 600. Why does it still melt at 400? 450. Then click. Suddenly the whole thing's full of crystals. It's supercooling. So it's like it's supposed to crystallize, but it's a delay. It's supercooled. So all those things we can understand, and we basically understand the process of chondrule formation. Now, what we don't understand, and where there's blood on the floor, to be quite honest, what caused that flash heating? That's where people get mad at each other. What caused that flash heating? We've also got some age data. These are not the best data to make this point, but I happen to have the picture. We now know that the chondrules, this is age worked out from the iodine xenon decay series. Don't need to get into too much detail. These are different textures of chondrule. But the first formed solids in the universe are here in the solar system, are here at about -5. Oldest material in the solar system is about there. Oldest melted asteroids are about there. So most of these chondrules are about 4 million years younger than the first solids in the solar system. So I better speed it up a bit here. I've got 7 minutes to do 2/3 of my talk. But what else is new, you know? Metal. Here are the metal grains that I was telling you about. Lots and lots of metal grains here. And so next thing we have to explain, we have to worry about, is how we vary the amount of metal in relation to the amount of silicate. That's what appears to have happened. There's a metal grain I worked on in England in my days when I was a metallographer. Spent 3 years pretending to be a metallographer, material science. And you can see inside the grain there's all sorts of cool things going on where you've got compositional profiles. And again, those are all pretty well understood, pretty nicely worked on. So, just summarizing some of this textural stuff, we have chondrules. The chondrules have diameters in this range, and we have metal grains. They have sizes in this range. But what we see is in these different classes described in terms of chondrule abundance, chondrule chemistry, volatile element patterns, siderophile element patterns, these different classes all have their own mixture of metal and chondrules. This is a well-known observation which is very little thought about, but I think is actually critical. Not only did we make the different classes by the different chondrule mixtures and by the different metal-silicate fractionation, we fixed in different size ratios of those objects. So this is telling me that the relative size of the metal and the chondrules is somehow or another giving us the different properties of the different classes and therefore the different chondrite classes. I think this is a key observation which has been very little worked on. All right, do you want a summary? Or should we skip it in the interest of time? This basically says everything. Chondrules are old, chondrules are solar, subtle differences that give classes, lithophile, siderophile, element patterns, cosmic set. I didn't really stress that, but I guess it was implicit. We're not looking at any familiar kind of geological process. These are not metamorphic rocks or igneous rocks or whatever. They are some sort of mixture of solar stuff. People talk about cosmic sediments. Size sorting of chondrules and metal has been important. That's the slide I just showed you. Chondrules formed about 4 million years after the oldest solids, and we understand a lot about the mechanics of making chondrules. Slide I just showed you. Chondrules formed about 4 million years after the oldest solids, and we understand a lot about the mechanics of making chondrules. So, all right, here's the traditional view of the origin of the solar system. This story, in one way or another, has been around now for many, many decades. We have density increases, we have rotation and gravitational collapse going on concurrently. We end up with the fried egg structure here, and then we get some polar movement, and we end up with the solar system. says everything and it says nothing, right? I'm offending some astrophysicists. I won't worry about that. That's too much detail. Now, all right. We've been to asteroids. Very, very important. We've actually been to a lot of asteroids. The asteroids have varied enormously in size. But they have a couple of things in common, which I think are important, which is important to note. They all have craters. They all have lots of craters. They all have subdued textures. There is a layer of dust covering everything. So that there is actually a cutoff on the size of craters you can see. Some craters on these asteroids are so small they've been covered in regolith you can't see them anymore. Regolith is the unconsolidated dusty layer. Number one lesson here, heavily cratered, impact, and very thick, unconsolidated, dry regolith. That has major ramifications for what I'm talking about. Big craters, you can make impact melt spherules, otherwise known as chondrules. Right? Okay, I'll raise a few heckles there. Hackles. Thick regolith, that means when an impact occurs, unlike the view about 20, 30 years ago, the energy will go into the regolith. If you impact a solid piece of basalt, hard rock, most of the energy comes out in the fragments that get thrown out. Right? Most of the energy comes away again. If you have this thick unconsolidated regolith, most of the energy goes into the object. Okay? So this is one of the problems people used to have, is how do you melt these things? The energy gets thrown away. No, the energy goes into the regolith. And I can show you graphs and what have you. No, wrong. See, I knew that one. Okay, this is making this point. All right. So another pause for thought. Chondrule formation, metal-silicate from fractionation. I said that we understand the mechanics of making chondrules. What we do not understand is the flash heating event. I have a colleague who I shared an office with at one point in my career who loved to catalogue, and he went through the literature and he counted 72 theories for making chondrules in this nebula-like environment. Now this is a few years ago, so I think the number now might be somewhat higher. But I won't go through all the details, but if you have an astrophysical environment in mind and you think about what could flash melt little bits of solid, there are 72 theories floating around. What does it tell you when you've got a lot of theories? None of them work. Harold Urey, on the other hand, in the 50s, gave us the idea that chondrules were formed by impact melts, that you had an object hit the rock, melted the material at the point of contact, that got thrown out into space and solidified and crystallized and made chondrules. That theory became unpopular when people started to think about this argument I've just made about impacting a solid object does not make much melt. It makes a lot of highly energetic fragments flying away. But we now know that's not true because we now know these things have thick regoliths. But now you look at the sort of how do you make chondrules on a parent body, we've got 4 theories in the literature. This actually is encouraging, right? Only 4. Volcanism, you can get spherules thrown out of volcanoes. Pelly's hair and all the rest of it. These are not volcanic rocks. These are cosmic, these are solar stuff. They have not been through any kind of igneous process. Nobody would call them volcanic, right? Not these ordinary chondrites. Those things from Mars and the Moon, yes, but not these. Impact onto a dense object has the energy distribution problem. To get over the energy distribution problem, somebody suggested that you had melted targets. So you had all these melted asteroids, and that you impacted them, and so you didn't need to apply the energy. These were already melts, and they would spray out. Problem with that is that we're talking about solar stuff. We kept the composition close to solar. We didn't do any melting because that would change the whole composition. Iron would go down to the core and the refractory minerals would form crust. you get mantles. So we're not seeing, there's 100 reasons why this is not a good theory. So we're left with my favorite, which is impact into a asteroid with a very thick regolith. And you can do the calculations, and if you make a crater that's got the same diameter as the radius of the target, you will get the chondrules that cool in exactly the rate, or you get liquid melt droplets that formed in exactly the rate, that cooled at exactly the rate we see in the chondrules. Then there's all these problems which I've sort of alluded to, but haven't actually gone into in any specifics, that if you try and use those 72 nebula theories, we run into all sorts of problems. The volatile elements should not be there because they're high temperature. There should be no oxygen because you're in a hydrogen-rich environment. We see compound chondrules, chondrules hitting each other, dumbbell-shaped. So there's a high chondrule density. You wouldn't get that in an open nebula. No evidence that these are ever isolated objects in space. No cosmic ray tracks. No solar wind products. And we know they cooled very, very slowly. They did not cool in a vacuum. Right? Newton's law of cooling, they would cool in a certain way. One person said it, these cooled in a hot bath, to give you the slow cooling rates we see. Arguments that used to be used against an impact is this energy distribution idea. How do you get relative velocities enough to get you melts? You need at least 4 or 5 kilometers a second impact to get melting. Well, we now know that these objects formed 4 million years after the first solids. By then there was a proto-Jupiter. Jupiter was stirring up the asteroid belt, causing all sorts of chaos, and causing high-energy impacts. We now know from work done by Dan Sears at Michigan that if you have an asteroid and you throw these melt droplets into space, there's a number of possible trajectories they can take, but most of them involve the objects coming back onto the asteroid, so they don't get thrown out into space. And then my favorite, I suppose, looking at the meteorites, they all look like they came from that cratered, rough, beaten-up surface of an asteroid type of place. They are all breccias. I'll come back to that a few slides down the road. There's the oxygen isotope story. I'm going to skip this because of time, but John Wood said you can't float any theory without explaining the oxygen isotopes. So I've got some thoughts on that, which I will share with you if requested later time. But John Wood said you can't float any theory without explaining the oxygen isotopes. So I've got some thoughts on that, which I will share with you if requested later. Now let's think. So that's chondrule formation. I think they're impact melt spherules. Metal-silicate fractionation. Well, again, if you scour the literature, you will find that there are 6 methods that have been proposed for explaining the metal-silicate fractionation in a nebula-type environment. My feeling about most of these is some of them have not withstood the test of time. The ductility requires you cool through the Curie point, and there's some problems with that. Others well, I won't go into details, but let's just say those theories are out there. I think there are problems with most of them, but who knows? I guess the main thing is they're all or nothing processes. They give you all silicate, all metal. They don't give you these tiny fluctuations that we see on the Urey-Craig diagram. So I think we were looking for an environment where you can change the composition of the metal relative to or you can change the metal relative to the silicates, but only by small degrees. We don't want an all or nothing type theory. So we did a bunch of experiments where we flew undergraduates on the comet, and we gave them tubes full of sand and metal grains, iron filings about the size of the metal grains in chondrites, and sand about the same size as the chondrules. And we did a whole bunch of experiments to see how the size density sorting went in a microgravity environment. And this has all been, the mechanical engineers know all about this, or the fluid mechanics people know all about this. There's this equation, it's called the Ergun equation, and it basically talks about how metal, gravitational settling versus some sort of gas flow that would play off against that and would give you these patterns. And we did 2 experiments. On the first experiment, the first set of flights, you have about 20 parabolas on a 4-hour flight. We had all 4 undergraduates vomit. So that was my first result. I have this wonderful photograph of them all sitting with the bag under their face. The second experiment, we only had 1 give up their breakfast. But on the second experiment, we had Amber with this spectacular hair that went all the way down to the small of her back. And just as she got on the plane, she let the hair down. And so this picture has appeared in, goodness, it's a NASA photo. NASA owns the pictures because it was on a NASA facility. And so they're copyright free. So that picture has appeared all over the world in different adverts. Without credit, of course. But if you want a travel agency in Moscow to go out to the tundra, there's a travel agency that uses that as their. It is cool though, isn't it? Sort of really. See, well, there's Amber flying around. But she's got this rig with, in this case, instead of having 100 and something tubes, we had 2 or 3 big cylinders where we could actually get a video camera in there and we could watch the metal and silicate separating out. So we could document the process, and they both resulted in small publications. But the bottom line is, if you do the grain size sorting in a microgravity environment, using those parameters that we got from the meteorites, the chondrule sizes and the metal sizes, you can explain quite easily how you can get different classes of meteorites. And here's a sort of schematic that says, you got the higher density grains, but they're smaller. You've got the big chondrules, but they're lower density. And you can see how they would separate out during this microgravity processing. We had a gas flowing up there, but it could also just be the shaking. And you could make the different chondrule classes in terms of their metal-silicate fractionation by that kind of a process. Well, so I think the metal-silicate fractionation went on in a thick regolith due to particle density size sorting. I think chondrule formation is an impact melt process. If you look at the textures of the rocks, you stand back. Most people tend to look at these things with electron microscopes, but if you stand back and look at the big picture, A and B are from papers from the 19th century. Chermak, who's one of the scientists I mentioned earlier on, says the meteorites have a tufaceous texture. They look like tufts. And what are tufts? Tufts are these dry debris accumulations that you get around volcanoes. Well, I guess nowadays we'd probably say pyroclastics. But I'm not saying meteorites come from volcanoes. They certainly don't. But they are coming from that sort of dusty, sorted sort of material. You can see Mount St. Helens, the big objects at the bottom and the light objects at the top and so on. So that picture of Mount St. Helens going off is pretty much my view of the scenario from which these objects formed, rather than a Orion Nebula type thing. So it's this big impact plume, and that's where the chemistry and whatnot went on. Here's a meteorite from Fayetteville, Arkansas, my stomping ground for the last 30 years. So just outside the town in 1934, this meteorite fell. It fell in a field. It made the cows do strange things. The cows were walking in circles in this field. And the farmer came out to see what was making them walk in circles, and there was a hole in the ground with steam coming out of it. And he put his hand down in the hole. How many of you would do that? There's steam coming out of this hole. The cows are behaving strange. He put his hand down in the hole, and he came up with this meteorite. His name was Davis Richardson. He was a professor of maths at the university. So, but look at the texture inside, you see. Doesn't that look like a beaten up bunch of stuff from an impact environment? You have the light class of healthy meteorite, and then you have this dark matrix of like consolidated soil. And I'll just mention very quickly, because I want to please Peter, this is the meteorite we got a few weeks ago from the Gold Country. And you can see it also has this brecciated, beaten up, rocks within dirt type of environment, of texture. Well, just to getting to the close of my story, we've actually looked at objects from the moon, from Apollo 14. Apollo 14 landed at Fra Mauro, and one of the things that characterized the Apollo rocks, well, they're all breccias, they come from beaten up surface of the planet, was that picture up there. That's cathodal luminescence, again, electron beam, looking at the rock under electron beam. Everything, the rock itself, the igneous materials, the basalts and the other materials in there, the glassy stuff in there, they all have this characteristic blue luminescence of the mineral feldspar. The moon's famous for having like feldspar on the surface. But aside from that, sat in this sea of blue are the yellow bits. Can you all see the yellow bits? See the yellow bits? If you look at the yellow bits individually, they look like this. They, for all the world, as far as I can see, they look like chondrules. Right? Now, if you do the calculation, here's Imbrium. Fra was meant to be material thrown out by the impact that made Imbrium. And if you look at all the, if you do the calculation, this is all in the textbooks, the impact geology textbooks, throw a piece of material out from here, where does it land, how big is the particle, it all hangs together. The Imbrium impact produced all these spherules. But what's more important is that the flight time from the ejector to landing gives you the exact cooling time that you see from the Chondrule calculations. So these objects, because the crater's so big, because they traveled so far, they cooled relatively slowly in the same sort of bracket as the meteorites. For all the world, as far as I can see, these are the experimental confirmation that these chondrules in the meteorites were made by an impact melting process. But they did require long flight times, so you can't make them with any old crater. You have to have a crater whose diameter is comparable with the radius of your object to get those flight times. So we published that in '98. Well, that's pretty much all I have to say. Thank you very much for listening and smiling at least at my jokes. And if you wanna learn more, then you can go and give Cambridge University Press $164 to buy my book. If you don't think I'm worth $164, you can get the paperback that came out just a few weeks ago for $38. My publisher says you can't, but send me an email. Thank you very much indeed for your attention. That's a sore point.
Derek, if I can, I think we have time for a couple of questions. What sort of experimental proof could we do on asteroids using robotic missions to the surface of asteroids to reassure yourself that this model has got some legs?
I think it's certainly true that one of the big frustrations of studying chondrites is that we're looking at the jetsam. We're looking at the solar system jetsam. We're looking at whatever happened to float our way. And it's certainly true that you can make a very strong case for that most of these meteorites are coming from just a few objects. So it's stochastic, something ordinary chondrite-like exploded in our vicinity of the solar system to give us all these meteorites. So I think we don't have geological context for these rocks, and we don't know firsthand what environment was in which they formed. But the answer to your question, so we're going to learn a whole bunch of things, right? But for a start, we can see whether we get size density sorting through a thick regolith, and on what distance scale. Does that tie in with the theory that we've got here, and with maybe relative abundance of different chondrite types? Well, that's a bit flaky, but maybe there's something in there. We can see whether if you go from one place on an asteroid to another, where are the chondrules? Are they centered, like in the Lunar case, around with the Fra Mauro ejector for Imbrium? So are they sitting where they belong relative to the crater we think that formed them? And then there are things like, we should only get chondrules associated with the big impacts. So my prediction would be that on something like Matilda, where you have 5 of these impacts, all of which produce craters that are comparable in size to the target. I mean, that's amazing. How does an object survive that has 5 craters with a diameter comparable to its radius and still stay intact, still be there? It happened, right? So on that object, there should be a lot of chondrules. On an object which has only seen very small impacts, we probably won't see any. So I think there are thoughts you can have that you could, based on these theories, that you could test out by asteroid missions. And certainly a whole bunch of us have been involved in trying to get asteroid sample return missions into the NASA lineup, and now we have OSIRIS-REx. So to some degree we were successful.
What's the different temperatures of melting between the metallic part versus the silicate part?
Let me see. Metals melted about 1600 C. Silicates, depending on the one you're talking about, but if you're talking about the totally melted type of chondrule, the ones that went through the supercooling, they went up to something like 1900 C. And then the others were just a few hundred degrees below that.
Is
So
there
that's
a relationship between kinetic energy of impact or velocity of the impact and the temperatures generated?
I'm sure.
So
Yeah.
Do we have a rough idea that looks like? I mean, are these impacts capable of producing those kinds of temperatures?
Oh yeah. Well, I showed you the Lunar case.
Obviously so, but just, I mean, maybe the fact that these things did get melted gives you some sense of the both the velocity and the kinetic energy.
Yeah,
of the impact.
yeah, for sure. But you get impact melt spherules on tiny craters on Earth.
I'm sorry, say again?
You get impact melt spherules. You get these little tiny melts
Yes.
on really small craters on Earth. Okay. There's the Ries crater in southern Germany, Nordlingen in Germany. It's a very famous crater. Been very well studied. In fact, Willy Wonka and the Chocolate Factory, not the last one, but the one before, the final scene where they're going up in the elevator out of the village, little red roof. Anybody know what I'm talking about? That's Nordlingen, and it is in the center of a, what is it now, 10-kilometer crater. It's right in the center of this 10-kilometer crater. So that crater has been very well studied, and the church in the middle of the town is actually made of impact pressure. It's really weird. You think it's concrete, but it's not. Yeah, these great big glass blebs. But the answer to your question is yeah, that's a small crater, and it has small spherules. But what's really important is those spherules are not crystalline. The thing didn't have time, the melt droplets didn't have time to form crystals. So it's a matter of having enough energy and enough enough input energy to make a crater that's that big, so that it can create objects that are going to fly that long to get you the very very slow cooling rates that you need to produce these textures.
So you can actually maybe estimate a velocity and temperature of impact.
That's essentially,
for
yeah.
For every meteorite that you get based on its composition and
Well,
its characteristics.
yes, you're really talking about categories of chondrules, and the meteorites are mixtures of those. But the answer is yes, and we kind of did that in that Lunar paper. And you don't get an absolute scale, you get a relative scale. How big is the crater relative to the object it's formed on? Because the object it's formed on has got the gravity field that's controlling the trajectory. So you have to have a big crater, and you have to, in relation to the target object.
In relation to what?
The target object.
Oh, yeah, okay.
Bigger objects need bigger craters to get the same trajectories for the spherules.
So you can reconstruct the collision
Yes.
based on...
Two more questions, sorry. Two more questions just to wrap it up.
Hello, I'm over here.
Okay.
That 4 million year gap has been nagging at me, and so I was wondering if I could convince you to speculate wildly in public about that.
I thought I just did.
Yeah, well,
The 4 million year
why
difference.
exactly 4 million and not 6 or 3 or 2?
There's a bell curve, and that's the thing. That is one of the most interesting results to come out of the last couple of decades of radiometric dating in meteorites. The really cool thing is that we have discovered in the meteorites evidence for isotopes that are now extinct. Right? Now this is really cool, and it blows my mind. I mean, in fact, my colleague at Arkansas was involved in discovering the second of these extinct isotopes. He found evidence for plutonium-244, which has an 18 million year half-life. This gets you rather excited because, all right, these are sun stuff. The elements were formed by nucleosynthesis, went through the stars became supernovas, the material was ejected. In amongst all those isotopes that gets made are these radioactive ones like plutonium-244, aluminum-26, and so on. And the rock formed, it became solid, and it started trapping the products of radioactive decay. Now, that means if you're looking at the decay products of an 18 million year isotope, it means that rock formed within 18 million years of the supernova going off.
Really quick.
Yeah. Now you're talking astronomical phenomena here. You're talking about a supernova going off here, and then a rock forming here, and that rock formed that quickly. So I mean, you're impressed with 18 million years, right? Now, what if I tell you the same story is true of aluminum-26? And aluminum-26 has a 3/4 of a million year half-life. Hey, now this is getting crazy, right? The supernova goes off, and within a few million years, typically they say like 20 half-lives. So within 10 million years of the supernova going off, you've got the rocks forming and trapping the decay products of the aluminum-26, which is magnesium-26. I mean, this is something going on here which is mind-blowing. Now, when I tell you that there's also sodium-22, I think I got that right. Neon. No, there's neon-22, which is a strange isotope produced by the radioactive decay of sodium-22, the beta decay. That has a 2.5 day half-life. What the hell is going on? I mean, I don't know. But anyway, I'm talking about extinct nuclides, and I'm getting off the topic of your question. Your question was, what do we make of this 4 million years? And the answer is, if you use these incredible chronometers, highly precise, amazing work, but if you use these chronometers, then the oldest materials we have in our lab formed 4 million years earlier than these chondrules that we're talking about today. 4 million, there's a bell curve, maybe it's 5, maybe 6, but they tend to hover around there. And then there's questions of what is the real decay constant, and we don't always know these decay constants that well, believe it or not. And well, this is an isotope we can't study in the lab. So working out these, so every now and then somebody comes up with a new decay constant and the number changes to 6 or something. But anyway, it's short. And I think that's important because this argument that if everything's going around in circles in the asteroid belt, the relative velocity of one object against another one is 0. So how can we shake things up to get significant impact? And that was one of the arguments against an impact origin of chondrules. So there aren't energetic enough impacts. But now that you put 4 million years in there, it took, as I understand it, we've got some experts on this in the room, or we did have before they left. I suppose they're still experts. But, they're telling us that the proto-Jupiter formed, and then it formed a core basically by what do you call it? Collapse. Falling by gravity, just collapsing, free fall, like a free fall collapse. In other words, a very, very fast process. So within a matter of tens of thousands of years, you went from having a diffuse blob of gas to a huge planet, a huge protoplanet. And so that huge protoplanet formed within, as I say, 30,000 years of T0. So that object was there before these chondrules formed, right, by almost 4 million years. So by the time these objects formed, Jupiter was there with all the resonances going on throughout the asteroid belt, and so the asteroid belt was getting a real good stirring up by this gravitational interaction with the proto-Jupiter. So by then, you were getting 6 kilometer a second impacts quite readily. There was a period in there where impacts were very energetic. So I think that's important because one of our problems, how do you get the relative impact velocities, is now taken away. The answer is the asteroid belt was being stirred up, and you were getting these 6 kilometer a second impacts. So does that work for you?
Okay. Derek, a real quick last question. Frank Hsu from Berkeley, I think it was.
Yeah.
The model he had for chondrule formation of forming close to the sun and being shot out and then mixed.
Yeah.
Or I can't remember those chondrules are just various minerals.
He was talking about the refractory inclusions that I haven't mentioned. But the problem with that kind of theory is that you are making these chondrules in a hydrogen-rich nebula. And they won't have any of the properties that we see. Yeah. The other thing is, if you, I mean, this is a different topic in a way. I think these refractory inclusions that I didn't really talk about, I think of as being superchondrules. Right? I think whatever the chondrule forming process was, if you take it that much further, you make the refractory inclusions. And we got intermediate objects. We've got the olivine amoeboid objects that are the bridge. So I think if they're coming out of some central source, like the sun spewing them out somehow, then they should be sprinkled throughout the asteroid belt, throughout the solar system. And in fact, the refractory inclusions are really only seen in any significance in one class. So you've got a targeted process. You've spewed this stuff out from the sun, and then you've made everything land on this one asteroid. So it's got to have been a local process. I get a mug.
Yes, Derek. Derek, we have a special mug. I don't think it's solar composition anymore. There's a lot of glass though on the front. So
very good.
Please join me in thanking
Thank you very
Derek for
much.
his great talk.
Thank you.